Okay, we have here a pretty interesting integral, and you may think, no, this is actually a really boring integral because it's just a simple trig identity, and then we integrate it, and then we're done. Well then, okay, but to spice this up, I think what I'm going to do is let's do this a different way. Instead of using normally what we would do here is we would do the power reduction on this, right? We could rewrite this as 1/2 minus 1/2 cosine of 2x, and then it's easy to integrate. We evaluate, and we're done, but it's boring. So let's not do that. Let's erase this instead. So what I wanted to do instead to make this more interesting was let's do it with King's principle. So what I'm going to do is I have a particular substitution I want to do. Adding my bounds together, 0 plus pi over 2. We're going to have pi over 2 minus x. And then isolating x, we're going to have x is pi over 2 minus u. And our dx is really messy. And our dx is equal to minus du. So I'll go ahead and we'll make this substitution. And what's going to happen is it's going to flip these bounds around. We're going to end up with 0 for our upper bound when we plug pi over 2 in here. And then when we plug a 0 in, we end up with pi over 2 for the lower bound. Now on our sine value, what's going to happen is pi over 2 minus u here. And then again, we have a minus sign on our du. What I can do is take this minus sign, bring it out front, and we'll use that to flip our bounds here. So we're going to put it back the way we had it initially. Okay, so we're going to be back to 0 to pi over 2. Let's get rid of this, make it go away. And then this is actually pretty nice because you may notice this is actually the complementary angle formula. All it does for sine and cosine, it flips the sines to cosines, the cosines to sines. So this is actually going to be the same thing as cosine of u. Sorry, I forgot this is squared. So there's the sine squared there. So now when I rewrite this, I'm going to write it in as cosine squared. But instead of using u, I'm going to do a variable change all in one step. And that is because it's a definite integral. So I can change the variable if I like. So we're going to change it back to x. And I'm doing that because my intention is to add these two integrals together. So our original integral was I. And then this is I after we did some work. And what I'm going to do when we add them together, we're going to end up with 2i. Now we're going to have these bounds, the same bounds from 0 to pi over 2. And then we're just adding sine squared and cosine squared. So we end up with sine squared x plus cosine squared x dx. And what do I do now? Integrate? No, not quite. There's some good news here. You may notice this is sine squared x plus cosine squared x. Well, we have the identity that this thing is just 1. So actually, this thing simplifies really nicely. We're just integrating 1 dx. Well, that's going to integrate to x, just evaluate it from 0 to pi over 2. We just have to keep in mind that we have 2 copies here. So let's evaluate this. So of course 0 is going to be 0. So we plug this in. We're just going to have pi over 2 over here. And we just need to divide off this 2 in order to get our final solution. Divide by 2 on both sides. And what we're going to get to finish it off is just pi over 4. Oh, what the hell happened? So for our final solution, oh, that's terrible. And so for our final solution, we have just pi over 4. That's it. Fun, kind of unnecessary problem. So we'll stop it there. Thanks everyone for watching. Have a good day.